Good morning, everybody, and thank you for joining us today for this webinar on IGEM's peer review consultation for gas quality and changes to the gas safety management regulations. Energy Networks Association and the Gas Goes Green programme team at ENA are delighted to be supporting this vital industry engagement process that IGEM are undertaking, and I'll say a little bit more on exactly why that is in a moment, how we see this work as important and enabling and an enabling step in delivering net zero. First, though, here are some housekeeping matters to run through whilst we are getting a few more people joining the meeting. So, firstly, I'm Tom Collard, the Gas Goes Green programme lead at Energy Networks. If you have any technical issues during the meeting, please do email gasgoesgreen@energynetworks.org and we'll do our best to resolve those. You'll notice that your microphones have been muted. Please do ensure that your cameras are off as well. That helps bandwidth issues and maintains a good connection for everyone on the call. Please do also make use of the chat function. This will be running throughout the meeting, and we're really looking forward to getting as many comments and questions as possible through that. We will publish a collection of responses shortly after the meeting, and do also, as well as asking the questions through the chat, be sure to raise these through the consultation process itself, which we'll detail later on. The webinar is being recorded, and a link to it will be made available shortly afterwards, so you can share that with colleagues. If you are having any technical issues and aren't able to use the chat functionality, do try joining Teams meeting via the web app using incognito or private browsing. That we found often resolves those issues. So, moving on, as you will likely be aware, ENA and its gas network companies have been supporting greening of the gas grid for many years now. The gas networks have supported more than 110 biomethane connections to the gas grid, commenced practical trials of hydrogen blending, and are developing dedicated hydrogen networks. We formed the Gas Goes Green programme to build on these successes to date and to put forward an integrated plan for the gas networks that sets out the role we see them having in delivering net zero. And the programme is a joint initiative between ENA, National Grid, Cadent, Northern Gas Networks, SGN and Wales and West Utilities. Through the programme, we are bringing together the engineering expertise of the gas network companies with the wider energy industry, policymakers, academics, to make the changes that we see as being necessary to move the network infrastructure from one that's delivering methane-based natural gas today to zero carbon hydrogen and biomethane in the future. And the Gas Goes Green programme has 6 work streams, with the second of these, as you can see on the screen there, focusing on gas quality and safety. And the work that we're undertaking in regards to gas quality and safety is really to focus on ensuring that the safe transportation and distribution of hydrogen and biomethane can be made to the same quality and safety levels that we have today for natural gas. We know that if gas is to play a role in UK energy in the future, that existing gas legislation and regulation will need to change to allow for greater proportions of net zero compliant gases. So in this respect, IGEM's consultation, which you'll hear more about today, is really a crucial next step on the net zero pathway. Our view of the pathway, and indeed our Gas Goes Green programme and its deliverables for this year, were informed by research undertaken last year and the stakeholder engagement we did through that. And as we move to the next slide, you can see the changing composition of gas consumption that we envisage through this pathway to net zero, and the different steps we see as needing to be taken on that. So overall, there's a decline in the natural gas received by end users and an increase in hydrogen and biomethane. And what I wanted to convey with this chart is that the changes to gas quality regulations to enable injection of low carbon and renewable gases are really a crucial first step of preparing for the transition. This, along with introducing some other policy required to support carbon capture and storage, or to mandate the requirement for hydrogen-ready boilers, for example, are really key enablers of those later steps in the pathway, as are set out in the bars on the top above the chart there. So it's really important that we progress this work. So as you'll hear more about today, the changes in gas quality regulations in that first part support the second part of our pathway, which is to facilitate more low carbon gases. We would also expect them to give confidence to investors finalising preparations for hydrogen projects, and that second step of the pathway then in turn enables the later step of the pathway to expand more supply. Biomethane from AD in this third stage really ratchets up here, again helped by changes in gas specification. And it's at that stage where development and testing of thermal gasification technologies for production of biomethane, which is crucial for the negative emissions that we see as being required to balance net zero, is at that stage when those first projects connect to the network. And then on to the later parts of the pathway from the 2030s, after expanding supply in step 3 on the chart there, we need to expand the demand base. So it's at this stage where we see hydrogen clusters develop with anchor customers in industry and transport. And then at this time, hydrogen storage also develops alongside those clusters to ensure supply. And then in the latter stages of the pathway, from the mid-2030s onwards, this is where increasing low carbon gases are on the network, and these initial hydrogen are expanding and merging to form hydrogen zones. And this takes us to part 6 on the pathway, where the net zero energy system is achieved. And at this point, natural gas is only used for the production of hydrogen with CCS. So I wanted to set out that gas goes green vision for meeting net zero, really to provide the context for the discussion that we're about to have. So moving on to the objectives for today. In hearing from the expert speakers IGEM and ENA has lined up, we'll understand the timelines for gas safety management regulation changes, understand the timelines for IGEM's gas quality standard, understand the evidence base that's been developed to date, and also we'll hear about the gaps in understanding, where through their consultation, IGEM would really like to hear from you all. So, as you can see on the agenda on the next slide, we really have gathered together some of the UK's leading experts on this work, and we have a packed agenda for you. First up, we're going to hear from Ian McCluskey, who's the Head of Technical Services and Policy at IGEM, and Ian's going to provide us with an overview of the new IGEM gas quality standard for net zero emissions. We're then going to hear from Dave Lander. Dave Lander Consulting has been working on a number of elements in regards gas quality, and he's going to discuss the Dutton method. Dr. Martin Brown, Principal Specialist at DNVGL, will then present on the domestic customer's case for change. And Dr. Sarah Kimpton, Senior Principal Consultant at DNVGL, will then discuss gas quality variations and industrial and commercial customer case for change. And we'll then hear from Dave Lander on the network safety impacts, before we then finish with a further Q&A hosted by Ian. So, final thing from me is just to remember, please do ask questions throughout any of the presentations via the chat, And as I say, we'll do our best to answer them after each presentation, and then there will be that further opportunity at the end. So without further ado, I'll pass to Ian McCluskey.
Okay, thank you, Tom, and good morning, everyone. It's great to see actually so many people on the call this morning, and thank you all for coming along. So I'm Ian McCluskey, I'm Head of Technical Services and Policy at the institution. I'm here today to introduce the new gas quality standard, and I'll describe the process it's taken us some 4 years to reach this stage and summarise the changes which are being proposed in the new standard. This is an extremely important stage in the development of the standard. The standard has been prepared based on the scientific evidence and the debate by an industry working group. And we're now at this industry comment stage where we welcome your comments and on the proposed changes, and we invite you to review the evidence which supports those changes, some of which we will be presenting to you today. Next slide, please. But first, I'd like to begin with a brief introduction to the institution, as it's important to understand our strategic and historic role in supporting the industry as it has evolved through significant periods of change. Formed over 157 years ago, the institution is among the oldest of engineering institutions in the UK and was awarded a Royal Charter in 1929. We're a global membership organisation of individuals and registered companies, and we're also operating for wider public benefit. We're also licensed by the Engineering Council to award professional titles for engineering technician, incorporated engineer and chartered engineer. But perhaps what many will know IGEM for is the publication of a suite of standards which are respected by industry and by regulators, covering engineering requirements from breach to burner and everything in between. Now, we've been publishing these standards since the 60s, where safety considerations are paramount. They're developed through a quality assured governance process, and the standards are drafted by practicing qualified engineers, scientists and professionals in their own field, both members and non-members, through expert panels and working groups, which allows for robust debate and peer review. But once past this stage, and the experts have agreed on the content of the standard, the governance process requires this wider industry consultation, the period that we're in now. They're then submitted for further scrutiny through IGEM's committee structure and approval prior to being published. An extremely important point to note is that IGEM standards are continually reviewed and, where required, updated to reflect the latest research, innovation and technological developments. Next slide, please. So having set the scene for the IGEM standards, it's important to understand, well, why an IGEM gas quality standard, why now? It's no surprise, and everyone understands now, that gas supplies have changed dramatically since the 70s, and the current requirements for gas quality, which was simplified in Schedule 3 of the Gas Safety Management Regulations, were developed by British Gas Research in the 70s and the 80s, and based on the requirements for safe combustion of domestic appliances that were in use at that time. The details of that gas quality parameters were then published by IGEM, or IGE back then, in 1984. And you'll hear more on that and the specifics and the details from Dave Lander later. So as we look to the supply study, the picture is obviously dramatically different, with less than half the gas coming in from the North Sea as the UK CS supplies dwindle and reliance on more and ever more imported sources of gas. But also, as we move forward to the journey to net zero, as Tom has explained, we're going to be introducing more biogases, and more hydrogen will become part of the gas supply mix. And all these gases, as you can see from the chart below in terms of the WOBE limits, have got varying different degrees of characteristics, but importantly of WOBE limits as well. Next slide, please. So in 2016, in meetings which were held with Ofgem, Health and Safety Executive, DEC, now VES, and IGEM, to explore setting up an expert working group to investigate the potential changes to gas quality, and it was agreed that IGEM would develop a new industry standard that would meet the current and future gas supplies for the UK. Now, at that time, it was proposed to initially examine the evidence base for the changes to the upper WOBE limit based on extensive research undertaken by SGN on the Oban project opening up of the gas market. The expert working group would then later consider examining the evidence for the widening of the lower WOBE index and other parameters. And it was essential that the review process consider the previous studies in this area, plus also look at the current and new research to consider not just domestic, but also assess the impacts of any changes on industrial and commercial equipment, and also assess the impacts for network safety. Next slide, please. So the gas quality expert working group was set up, made up of subject matter experts, some of whom you'll hear from today. And on this slide here, you can see an example of those organisations, stakeholders that are part of that expert working group. It includes the Health and Safety Executive, gas producers, networks, as well as organisations representing appliance manufacturers. I'd like to take this time to thank all members of the expert working group for their support and contributions to drafting of the standard. And in particular, I'd like to thank Gus McIntosh of SGN, who's chair of the working group. Next slide, please. So the primary objective of the gas quality standard for the expert group is the production of an IGEM standard covering UK gas quality specifications in order to facilitate a change from GSMR that reflects the declining supplies in UK CS and the available alternative sources of gases. The standard aims to facilitate the safe injection of a wide range of gases, securing UK gas supplies without the need for additional processing, and help to facilitate decarbonisation by reducing processing emissions and allowing more hydrogen into the network. And it's important to remember the gas safety management regulations are primarily intended to ensure the safety of the public, and that will continue to be the primary aim of the new gas quality standard. Next slide, please. During the period of the review for the past 4 years, we've researched extensively many existing reports in this area. And on this slide, you see some of the reports that we're going to be outlining today include, for example, the SGN opening up of the gas market that I mentioned earlier is perhaps one of the most extensive areas of research ever undertaken. SGN's operating under an exemption to supply 4 Scottish towns with high WOBE gases provides an evidence base for domestic and small commercial appliances, some 8,000 properties, some 11,000 installed appliances, and since the project ended in 2016, have continued with random checks totaling about approximately 4,000 checks. Another important report is the industrial and commercial research into appliances and applied research into the effects of the wider range of WOBE gases that was undertaken. There was also an impact study which examined the lower WOBE index gases. The aim of that study was to provide the evidence of the impact of utilisation of gas of quality down to the existing emergency WOBE index lower limit. Another important report that Dave Landau outlined is that some 40 years since conversion, UK appliance types and designs are now widely different, and it is therefore considered appropriate to revisit the Dutton approach and assess its usefulness for existing and future gas supplies. And finally, Dave will also talk about the work and the study which was comparing pipeline fracture propagation risks from natural gases of differing WOBE index, and the report examines whether there would be an increase in risk of pipeline fracture propagation in the event of any pipeline failure, and details an assessment of the change in risk associated with the conveyance of natural gases of higher WOBE gases. Now, next slide, please. So now we've reached, as I've mentioned, this key milestone, which is the industry-wide consultation stage. And to support the consultation, we published this evidence report. It's called a key step on the pathway to net zero emissions. And the report explains the proposed changes to the gas specification, which I'll outline in a second, and provides reference to all the extensive supporting technical evidence. The report outlines the existing gas quality issues, the updated Dutton interchangeability diagram, the case for domestic and industrial and commercial appliances, as well as the impact on network safety. Now, the proposed IGEM standard will be a dynamic framework for changes in gas quality, but the enduring safety of domestic consumers will be paramount, and the HSE will continue to have a veto on any proposals that could compromise safety. Next slide, please. So I'll now introduce the changes that are being proposed, and within the report there is a table, and that table provides a summary of the proposed changes from Schedule 3 to the new IGEM standard. I've highlighted those in red. You'll see there's no change to hydrogen sulfide content. There is no change to total sulfur content. Or at this stage, though we are preparing for it, there is no change to hydrogen at this stage being proposed. That still remains at 0.1%. Oxygen content will move up from 0.2 to up to 1% for networks operating below 38 bar, which reflects the current class exemption for biomethane. We'll also widen the WOBE index by decreasing the lower limit and increasing the upper limit. So the decrease to the lower limit from 47.2 to 46.5 megajoules per cubic meter. We'll increase the upper WOBE index limit from 51.4 to 52.85. The incomplete combustion factor will be removed. And on the next slide, we'll continue with a summary of the changes. The suiting index will be removed by the proposal. And having removed those interrelated safety parameters, we're simplifying in the proposal the GSMR interchangeability diagram to a WOBE index of the range that we described and introduce a new maximum relative density of 0.7. And finally, removing the upper and lower emergency limits, as these will now become the normal limits. Now, that's the summary of the changes. On the next slide, I'd just like to highlight the link to the website. Now, IGEM's website has the evidence report. It also has the standard. It has a governance document on there for changes as well. The consultation period and an example there of the link to the website. Please, we welcome your comments on the draft standard, particularly any comments relating to the scientific evidence which can be found on that link also. And that consultation period ends at the end of July, on the 30th of July. So thank you for that. That's hopefully giving you, setting the scene for what's going to be presented to you in the sessions that will follow. And I'd now like to introduce Dave Lander. Dave Lander is going to pick up on the Dutton Revisited, and I'll manage the questions through Q&A at the end of Dave's session. At the end of each of the sessions from Dave and Martin and Sarah, I'll do some Q&A session after that. In the interest of keeping to time, I may need to not answer all those questions, but as Thomas said at the beginning, we will respond to all the questions, but please go onto the IGEM website, put in your comments there as well, and we will respond to all the comments that are being made. So Dave, if you'd like to pick up from here, thank you.
Thank you, Ian. Good morning, everyone. Can we have the next slide, please? Okay, this is just an overview of the topics I'll be talking about. So initially, I'll go back and talk a little bit about the UK approach to natural gas interchangeability as it stands at the moment, a little bit of historical context, and in particular discussion of the appliances generally installed at the time. I'll also give you a description of the Dutton method. It's quite a complicated method, so it will be a simplified explanation. We'll be talking about this thing called the equivalent mixture and the parameters that Dutton used to characterize appliances. Okay, next slide, please. Okay, so a little bit of discussion on the choice of the limit values that Dutton made then, and maybe a commentary on what we're proposing now. And probably the biggest change is the actual second of the two interchangeability parameters that are used. So we'll be switching or proposing switching from Dutton's GSMR interchangeability diagram to a simplified diagram that involves WOBE index and the relative density. Next slide, please. Okay, so from a historical point of view then, most of this work really started in the 1970s and the 1980s. In that situation, we had southern North Sea gas fields dominating gas supplies, but it was anticipated that there would be a decline in those supplies, and those will be replaced by other sources, which will be different and more variable. And essentially those were northern North Sea supplies, which tended to have a higher WABI index. But also Dutton noted at the time that eventually these would be replaced by manufactured SNGs. That's probably not quite the scenario that we actually panned out. I think we were anticipating in the late 1990s for substitute natural gas to be made in quite a significant proportion, but that hasn't happened as of now. Okay, so the were drivers for interchangeability methods. So principally safety. Domestic appliances essentially have very limited tolerance to variation in combustion characteristics. So effectively you have to make the gas to suit the appliance and not vice versa. There's also a commercial driver, of course, and that is simply that you want to treat gases as little as possible in order to make sure that they're interchangeable. Next slide, please. So effectively, British Gas Corporation adopted the approach that was developed by Brian Dutton from the Watson House Research and Development Division. And there were a series of research papers that were published, but summarised in what is now the well-recognised IGE Communication 1246. So that was published in 1984, but based on experiments that were carried out in the 70s and the early 80s. It was a new approach at the time. Prior to then, appliance effects and flame phenomena that were related to gas composition were essentially related to functions that were effectively measured and very often based on properties like burning velocity. But Dutton's approach was to relate those to compositional variations, and that was also consistent. You have to remember as well at the time that there were significant developments in gas analysis, and some of the early process gas chromatographs were being developed at around that time too. So it was a convergence of the ability to analyse routinely, cheaply gas analysis and use that data to correlate properties of the gas being conveyed. And Dutton's approach was effectively implemented into the gas safety management regulations in 1996, and that essentially was at around the time of the initial start of gas privatisation too. Next slide, please. So in developing his approach, Dutton recognised that there were three key combustion indicators, poor combustion indicators. First of those is incomplete combustion, where significant quantities of carbon monoxide can be formed in addition to carbon dioxide. And that's generally seen at high WABI index, and to a certain extent at low WABI index. The next poor combustion issue is flame lift. That occurs essentially when the flame speed becomes quite low, and the speed at which the flame burns becomes lower and lower, and the flame tends to lift off the burner tip and ultimately can extinguish. And generally you see that at low WABI index. And the third aspect is sooting, and that's generally seen with higher density gases which contain higher hydrocarbons. So you get small particles of carbon which give you a sort of yellow tip flame, and ultimately you can get deposition of carbon on things like radiant gas fires. Okay, next slide, please. And so those three poor combustion indicators were tested by Dutton, and he carried out testing of a variety of appliances that would demonstrate the three poor combustion indicators. Okay, and so for his incomplete combustion, Dutton looked at water heaters, instantaneous water heaters, very common appliance at the time. And for flame lift, he looked at cooker hobs. And for sooting, he looked at gas fires, radiant gas fires. Next slide, please. And it's the performance of those appliances which really set the basis for the limits in those particular properties. So I mentioned that the Dutton approach uses gas composition, And the first step is to simplify the gas composition. Natural gas is quite a complicated mixture. It contains up to and more than sometimes 11 components, and so in order to get some easier interpretation of the data, he converted the gas composition, sometimes 11 component gas mixture, into an equivalent mixture of methane, propane and nitrogen, and in some instances hydrogen. This process of converting to an equivalent mixture is a well-recognised approach, and is used quite often, particularly in reservoir modelling, where you can simplify a composition and you get equivalent properties for that particular mixture. And to do this, Dutton replaced all of the hydrogens with an equivalent amount of methane and propane. Any inerts were adjusted, were converted to a single nitrogen component, which preserves the Wobbe index of the original gas mixture. So once you've carried out this process, your 11 component mixture, or sometimes more than that, is converted to a mixture of methane, propane, nitrogen, and possibly hydrogen if there is any in there. And so you have a simplified, what's called equivalent gas mixture. And in carrying out the testing, he identified 3 interchangeabilities that could be related to the composition of the mixture. The first was what's called the incomplete combustion factor, and I'll talk a little bit more about that later. But that characterises the formation of carbon monoxide. Then there's his lift index, which characterises the propensity of the flame to lift from the surface of the burner tip, and sooting index, which is the propensity of the gas mixture to form soot. And it's possible then to compare all of these 3 against and develop suitable limiting values in those particular properties. And by defining those limiting values, you can effectively bound gas composition for normal, and in some instances for emergency use only. Next slide, please. So Dutton effectively characterised limit values for all of these properties, but it's actually quite nice to be able to visualise the region in which normal operation is preferred. And he did this by developing a diagram which you plot Wobbe index and what's called the P and N number, which is the sum of the nitrogen and the propane in this equivalent mixture. And that allows you to sort of visualize areas in which gas would be normally deemed to be interchangeable. So this is the simplified version, which was adopted into the gas safety management regulations. So that central region is where normal operation gases will be considered interchangeable. And that effectively then is bounded by 4 surfaces. So the surface to the left, the lines to the left are essentially compositions of or that are feasible. So anything to the left of that line would be considered unfeasible unless there was a hydrogen gas in the mixture. So in the case of hydrogen-free gases, then those gases just don't exist outside that region. To the right, the sloping line that slopes from top left to bottom right is the sooting index line. So gases to the right of that line would generate effectively more soot than would be desirable. And then the upper and the lower blue lines are the limits that are formed by incomplete combustion on the top line, and that's the incomplete combustion factor, which is normally set at a value of 0.58. And that corresponds to a Wobbe index of roughly 51.41. So that red line, where the blue line intersects the red line on the left, that line there is for a Wobbe index of 51.41. So although there is a limit in the gas safety management regulations at the moment of 51.41, for most gases, they would be considered not suitable for admittance into grids at the moment, because they would hit the 0.48 ICF line before then. So although there is a Wobbe index limit, it's very rarely actually exercised. It's usually exercised by the control is exercised by the incomplete combustion factor. And on the lower blue line is the lower Wobbe index limit, which is currently set at 47.2. And Dutton set that not on flame lift considerations actually, but on heat service limitations. And that's really associated with the instantaneous water heater. So British Gas Corporation at the time would tend to have an increase in complaints about the water not getting hot enough. Okay, next slide, please. So based on the Oban work that we had carried out with SGN, what came out was a proposal to replace the Dutton diagram plot for Wobbe index against the PN parameter, but to replace that with a Wobbe index versus relative density parameter. There are two key reasons for that. Firstly, it's consistent with practice elsewhere in Europe, Western Australia and the United States. During the developments on the harmonised gas quality standard, European harmonised gas quality standard, the relative density Wobbe index plot emerged as the sort of favoured approach. The other reason for changing that is that the propane plus nitrogen, the PN, is not really an intuitive gas property parameter. It's quite difficult to calculate if you don't have a computer program to do that. It's not an intuitive property. Next slide, please. And you'll see also then that relative density is actually a good proxy for a PN number. So there's a direct correlation between that. And what that effectively means then is that you'll have noticed that effectively the shape of the Dutton diagram hasn't really changed when you replace the x-axis with relative density. Okay, next slide, please. So our proposal then is that relative density would be the second parameter, and we have set or proposed that the limit value should be set at 0.7, and that corresponds effectively with the European view, which developed when they developed the European standard EM 12676, which was subsequently adopted as a British standard. The Sutting index limit of 0.6 is not really a safety limited value, a safety related parameter. It's really to do with discoloration of radiant heaters, and that value there of 0.6 intersects with the 0.7 at around about that value that's indicated there. So the drop in the Wobbe index is quite small because the relative density constrains that drop quite effectively. There are very few gases that in the UK that would have a relative density greater than 0.7. Next slide, please. So this is the proposed interchangeability diagram that incorporates relative density limits and also incorporates two upper and lower Wobbe index limits. So in terms of the ICF limits, the ICF lines are close to horizontal anyway over the proposed relative density range, and so our upper limit is quite a tolerable simplification, and it's also consistent with practice elsewhere. Next slide, please. So as I mentioned, our first proposal is that the upper limit value will be increased to 52.85, and that corresponds to the current emergency limit value. Next slide, please. And the lower limit value, we're proposing that the lower limit value would be reduced to 46.5, which is the current emergency lower limit value. Next slide, please. So I'll just briefly cover sort of the logic behind setting those upper and lower WOBE limit values. So firstly, the upper limit, why should that be set at 52.85? Well, the main outcome from the IGEM project, the Opening Up the Gas Market project, was that domestic and small commercial appliances, when correctly installed, serviced and operated, can safely burn gas with a WOBE index up to 54.7. So that's quite a wide, quite a high limit value. It's consistent with the main findings of the gas qual studies. The gas qual study was that carried out, the pre-normative study carried out by a consortium of European gas appliance testing laboratories, and they fed all of their information for consideration by the working group that's developed the European standard on harmonised gas quality. So the OGM project produced findings that were consistent with gas qual, and equally those findings were consistent with earlier testing that was carried out by DNVGL in support of the UK tripartite gas quality study. Should also say that that's also consistent with even more recent studies that have been carried out by High Deploy, which is looking at addition of hydrogen into gas supplies. And again, there's a major body of work, technical work on appliances that are also justifying those limits too. Okay, next slide, please. It's also instructive to look at the origin of Dutton's incomplete combustion factor specification. So I'll just talk a little bit about incomplete combustion factor. So effectively, Dutton defined the incomplete combustion factor as the number of times that the CO-CO2 ratio in the reference gas has to be doubled to give you that you see in a test gas. And Dutton chose the value to characterise incomplete combustion limit as being the instantaneous water heater, which is often unflued. And typically what he found was that the CO-CO2 ratio doubled every 1.5 megajoules per cubic metre. Now today's equivalent appliance, I guess, would be the combi water heater, the combi central heating boiler. And if you do similar tests today, then typically what you find is that the CO-CO2 ratio doubles every 3 megajoules per cubic metre. And as a result, the correlations that Dutton produced that calculated ICF from composition didn't really correspond to today's appliances. Next slide, please. So what I've got here is an example of testing that was carried out by Kiwa during the Opening Up the Gas Market project. You see some typical results, and that again has been replicated in other studies too. And effectively, the bottom line, which is a combi boiler, you can see that the doubling of the carbon monoxide concentration occurs over a range of about 3 megajoules, not 1.5. And for the back boiler testing, it's even more than that. It's probably around about 6 megajoules. Okay, next slide, please. So Dutton's ICF formula, which appears in his paper, it's shown here. The important thing to look at is the 1.56 on the denominator, and effectively that's essentially what we're saying is that at the time Dutton found that instantaneous water heaters, the doubling of CO occurred every 1.5 megajoules per cubic metre. And what we find is that that formula doesn't really hold for today's appliance. So on the graph on the right, so the dotted lines corresponding to different ICF values. What we're showing is for those combi boiler and the back boiler, what the actual ICF found from the experiments was. So if you just look at the top line where the dotted line is ICF equals 2, then the values that you get vary from around about 0.6 up to about 1.1. So again, you're getting around about half the value that Dutton's formulation would have given. So today's appliances don't really reflect the Dutton formula. So next slide, please. So in terms of the ICF limit value itself, when Dutton was setting that, he was very conscious that traditionally at the time, rich gas limit was set to around about 5% over that of the reference gas, which is G20, which is pure methane. And it should have been 53.3 megajoules per cubic meter, although there is some confusion in the actual communication, as he cites that as the wet gas value of 52.1. But essentially, for the dry gas basis, it should have been 53.3. But in fact, what Dutton adopted at the time was a value of 51.2. And that really came about because of a survey of appliances that was carried out in 1978, which suggested that some appliances might have higher CO2 ratios than would have been expected. It was a very small proportion of appliances, but they chose to lower the limit value, not at, set it at 51.2 and not at 53.3. And the paper mentions that there was an expectation that they would review that at time. And there was a further survey of appliances, but again, they chose not to raise the value, the limit value. And that value of 51.2 is effectively close to the ICF equals 0.48, which is currently what's set in the gas safety management regulations. And remembering that this was done in the 1970s, it almost certainly corresponds to performance of converted Towns gas appliances. So if you remember, conversion from Towns gas to natural gas has started in 1968 and ended in September 1977. So it's quite a long process of converting, and at the time, almost most all of those appliances were converted. The churn rate was probably not high enough to get a significant proportion of appliances that were dedicated for natural gas. Next slide, please. So the lower limit, we're proposing setting that at 46.5. And essentially today's testing shows that CO emissions is not really a major issue at the lower WABI index concern, and it wasn't a concern when Dutton considered his lower limit values. The 46.5 megajoules per cubic meter corresponds to Dutton's flame lift limit, which is a lift index of 1.16, and that's just really when flames started to lift off the surface of a gas cooker. The existing lower limit value that we have in the GSMR is 47.2, and that was really set as a heat service limit. As I mentioned, it was set on the basis of instantaneous water heaters, and those water heaters would produce hot water on tap, as it were. And what British Gas Corporation found was that if the value fell to around 47, then there would be an increase in complaints from consumers. Today's a comparable device really, I guess, is the combi boiler performance. And we have looked at performance of combi boilers, and we don't think that there is a significant change in temperature of hot water between 46.5 and 47.2. So that's probably not an issue as far as heat service is concerned. And so again, we would be setting it on safety considerations associated with flame lift. Next slide, please. This is just a summary slide. And effectively, what we're proposing is adoption of limits based solely on the consideration of Wobbe index and of relative density. The use of incomplete combustion factor and propane plus nitrogen adds complexity without really any material advantage. The ICF calculated from the original Dutton relationship doesn't really fit with the performance of today's appliances. And it also provides us with consistency and practice with other countries, which is quite important now because you know, we are receiving significant quantities of gases through interconnectors and through LNG importation with other countries. The second change is the increase in the upper Wobbe limit value to 52.85, which is again more reflective of the performance of today's appliances. And it still allows us a safety margin of 1.85 megajoules over the results of in-premises testing in the opening up the gas market project. And finally, we're proposing decreasing the lower Wobbe limit value to 46.5. CO isn't really an issue at this level, and it's effectively Dutton's flame lift limit. And we're proposing that that's the appropriate limit. The existing lower limit value of 47.2 was really set on the basis of heat service, and again, that's on the performance of instantaneous water heaters, again at the time of natural gas changeover. Okay. I think that's my my session. I think the next slide will be just a Q&A session.
Thank you, Dave. There's been a few questions and lots of good activity on the chat as well. I think some you sort of answered as your presentation went on. There's been a question about sooting index and the evidence for removing that, Dave. I think you've sort of covered that. Just want to just mention reasons behind that.
Sorry, could you say that again? I'm sort of
the removal of the sooting index. What's the evidence behind that?
Yes, essentially, it's essentially the appliance that was used to indicate sooting or consider sooting index was the radiant gas fire, and the sole consideration was really the discoloration that you get when you have a sooting flame. So it's not really a safety related issue. Obviously, if there is sooting going on, then there is increase in CO, but the main consideration in setting that is the degree of discoloration that you would see on a radiant gas fire radiant. Again, the proposal is that a density limit of 0.7 would allow reasonable control of additional sooting concerns on such appliances. And in fact, we often think of the UK as having more stringent regulations, but in fact, in terms of sooting considerations, the current arrangements, we would normally permit more dense gases than 0.7 in principle, because the sooting limit takes you to a more dense gas, although there actually aren't that many examples of UK gases with density greater than 0.7. So we're actually slightly less stringent in terms of sooting considerations than the rest of Europe.
And just on that point, of questions coming from Shane Wilcox about, is it not possible for us to block a heat exchanger on an older style boiler?
I think that was studied during the DTI the DTI test. There were some studies of that. I think it's an order of magnitude difference, though, in terms of the propensity to block such to block such heat exchanges. As I stressed, the current limits are less stringent in sooting index for most of the range of gas quality. The 0.7 relative density limit effectively it makes it more stringent for most of the sooting index line, and so whilst there are not many UK gases that have a density higher than 0.7, there are some supplies in the south related to an onshore natural gas supply, and there have been no issues with such appliances then.
Okay, thank you, Dave. I think in the interest of moving on in time, I think any other questions that we've not got round to during this session, we will respond to it fully afterwards. But thanks for those questions. I'm now going to end this session and hand you over to Martin Brown, who's going to take us through the widening of the WOBI for our domestic customers case. Over to you, Martin.
Good morning, everybody. Dave's provided the framework really with regard to what the current limits are and what the planned changes are for the gas quality ranges that are acceptable in the UK. I'm going to provide you with a bit of a whistle-stop tour really in terms of providing an indication of what data was gathered and how that's evolved over the years to enable us to get to the position where we can make these judgments and provide you with background information with regard to what the impacts are with applying those different quality of gases, those different WOBI index gases, to a range of different appliances. I think some of the key messages that came out of the previous presentation are that the original Dutton work, the original gas safety management regulation, was built around the converted older style appliances, and clearly understanding how more modern appliances behave and what the implications are for those was a gap in the knowledge. But I think over the last 20 years we've actually been building that information base and actually extending that knowledge base so that we can actually provide now a very detailed understanding of how the emissions change as a function of the WOBI index and of different gas compositions. So can I have the next slide, please? So in overview, I'm going to touch a little bit about what WOBI index is and why it matters. Why we need to think about WOBI index in the first place from a combustion point of view. And there's been a question already on the chat about what the WOBI index is, and we'll clarify that now. It's equal to the calorific value divided by the square root of the relative density. It's a term that's used widely in gas quality studies, and I'll touch upon what it actually means a little bit later on in the presentation. Clearly, we need to think about how the different burners might respond to the changes in gas quality. So I'll put a couple of quick slides up regarding burner operation. And that links in really with the comment that Dave made previously, that for domestic appliances without sophisticated adaptive control systems, the gas has to fit the burner operation, the appliance operation. The appliances, they are quite sophisticated compared to what they were several years ago. But ultimately, they don't necessarily have the capability of actually adapting to extreme changes in gas quality. So we need to make sure that the appliances are set up and operating so that they can actually manage that gas quality range and burn efficiently and safely. And then I'm going to actually take you on the whistle-stop tour, really, of how the knowledge base is actually extended with regard to the practical tests that were done, and how we've actually ramped up, for want of a better phrase, the information that we have from the initial DTI work, which actually started off with 5 appliances being tested, through subsequent work with the DTI, and then onto gas qual, and then the probably the most significant test program that's been undertaken, which was done by SGN through their Opening Up the Gas Market project. So next slide, please. So why do we get hung up about what WOBI index actually is? Well, WOBI index is a key indicator of what is termed gas quality. And that's the ability of appliances or different equipment to actually burn gas. One of the nice things is that it's been adopted as a key parameter worldwide. So you can talk about WOBI index, and that's understood by a lot of combustion engineers, appliance development people, and gas quality people around the world. And it's very important for determining the interchangeability of these different gases. And why is it important? Well, it's an indicator of the actual heat rate going to the burner. This has been discussed in the chat as well, and if you've been following that, you'll have seen these discussions. Different gases with the same WOBI index should give the overall same burn performance on the same appliance. And one of the aspects that the WOBI index does link to is that it's actually related to the excess air that's available actually within the combustion system. Appliances will be set up for a particular excess air level, and that will be done to ensure good performance with the reference gas and enable the other test gases that are used to be burnt in those appliances, but still meet the requirements with regard to the certification standards to get that CE marking. So it's an important parameter, and it's linked primarily to safety and performance, efficiency, and operation. Next slide, please. So here's a quick schematic, a quick diagram with regard to how a typical partially aerated burner might behave as a function of excess air. On the y-axis, we've got the carbon monoxide content in the emission as a function of the excess air, which is labelled on the x-axis. Clearly, for stoichiometric combustion, you don't need any excess air, so you'll be down at 0 for that. Now, that would actually result in quite a high carbon monoxide emission. So, majority of systems tend to operate with at least 20, possibly even 30% excess air. Now, this is for a partially aerated burner. Here, we're looking at a typical flame, similar to what you would see on a Bunsen burner. So, it'd be a Bunsen burner type flame where you would actually have sort of a 2-stage flame, as it were. You have a primary zone and a secondary zone in that flame. The primary zone is often what is termed fuel rich, so there's not enough air to actually burn it out, and then the secondary zone is where the excess air comes in. And you can see that that type of burner would operate with very low carbon monoxide emission for excess air levels in excess of around about 20%. And it could extend for significant additional levels of excess air and cope with that quite admirably. Next slide, please. So superimposed on the initial diagram is what would happen if we had a fully pre-mixed burner. So that's where the gas and the air are mixed in a chamber below the burner and then burnt as a homogeneous mixture actually above the burner. So all the air that's required is actually provided through the burner itself. There you can see in the red line that you have different type of performance in terms of what sort of level of excess air would be the optimum for that particular burner. These burners are often used in condensing boilers. They're highly efficient, get good control, and give good emissions performance over a range from in diagram from about 10 to 45-50% excess air. The arrow that you see there, double-headed arrow, is an indicator of the range of excess air values as a function of the Wobbe index range that you might expect to see, or from the UK. So you could, if it's been set up correctly with the G20 reference gas, then you can actually get good performance over the whole Wobbe index range without any issues in terms of the carbon monoxide performance. Now that's for brand new appliances out of the box. It's not necessarily ones that have been installed and operated for a long period of time. It's not ones that have been misused or damaged in any way. So there's clearly a lot of variability that's required. But the safety record of combustion systems and the safety record of the gas industry is good. It's very good, in fact. And incidents related to poor combustion, although quite prevalent 20 years ago, 30 years ago, the numbers of people that are actually impacted by malfunctioning appliances is actually very few these days, thankfully. Next slide, please. So as I mentioned in the introduction, the level of understanding that's been developed over a number of years has ramped up significantly. It was recognised early on that the impact of different gas qualities on modern appliances wasn't fully understood, and the DTI were looking to evaluate what the impacts would be through changes of the gas quality range that could potentially be distributed in the UK. And so they've started some studies, sometimes called the tripartite studies, where they looked at different options with regard to gas quality in the UK. And kicked it off in 2004 with a pilot study and then the main study in 2006. The numbers that were involved there were, the pilot study was 5 appliances, the main study was 20 appliances. So it wasn't a large number of tests undertaken, but there were several, and several key factors that came out of that. A few years later, the EU gas cost study ramped it up even further and did 100 appliances. And then with SGN's opening up the gas market study, they looked in Oban at around about 2,000, in fact over 2,000 appliances. And then with the other Scottish independent undertakings that were studied, there were even more tests that were undertaken. So there's a good understanding now of what the implication is of different Wobbe index gases on a wide range of appliances, both ones that are in the laboratory but also installed in a real environment in Scotland. More recently, there's additional data that's coming out from High Deploy, and I think although we've not got a slide on that today, the general aspects with regard to that do reinforce the overall trends with regard to the emissions. And in addition to what's been going on in the UK and around Europe, there's a lot of additional work that's gone on in USA, China, Korea, and many other countries. Next slide, please. So now what I'd like to do is just take you through some example results. And as I say, I don't want to dwell too heavily on this, but I'll be picking a lot of trends and highlighting what the different studies have actually found as we go through. The format of the charts is very similar, and I'll just explain that in the first one, and then you can see how it cascades through to the others. So for the initial study, as I said, 5 appliances. They looked at a Wobbe index range from 46 to 56, so slightly wider than has been considered for the potential changes to the requirements, the regulations that we're proposing now. But that gives a bit of a safety margin in terms of the understanding. With regard to the studies, it was focusing on the carbon monoxide and nitric oxide emissions, and then also looked at efficiency, and the efficiency was measured by a flue loss method. Next slide, please. So here's a quick snapshot result of the 5 appliances. The 5 appliances are in the key on the right-hand side: condensing boiler, a water heater, a cooker, a fire, and a standard type boiler. The Wobbe index is on the x-axis, ranging from 46 up to 56. And the carbon monoxide emission is listed as a percentage on both of the left-hand and the right-hand y-axes. The left-hand one for most of the appliances and the right-hand one for the standard boiler. Within the main body of the chart, you've got two orange lines and a band. That's actually the current GSMR limit of 47.2 up to 51.4, as Dave highlighted. I just really want to draw your attention to the changes as a function of WOBE index as you go from left to right. For the majority of appliances, you can see that the emissions do go up in terms of carbon monoxide, although there are some scatter with regard to the ones from the fires. I think reflecting more the difficulty in actually doing those tests rather than any significant problem. The other aspect there is you can see that when you get gas qualities over sort of 53 mark, they do seem to start to increase quite a lot, and that's been taken into account with regard to some of the recommendations that we've come to with regard to the limits. The next slide, please. That shows the impact on the NOx emissions. Again, it's on the left-hand side, the NOx ppm as a function of the WOBE index on the x-axis, and you can see that the NOx actually increases as a function of the WOBE index. Next axis, next slide, please. And the flue efficiencies are reasonably constant actually, so there's not that much of a decrease in performance as you go down in terms of WOBE index, and not much of an improvement in efficiency as you go up in WOBE index. It's reasonably flat. There is a slight increase as you increase WOBE index, but not significant. Next slide, please. So the first DTI study was then extended a couple of years later and increased the number of appliances to 20. These are mostly used appliances, but there were one or two new ones that were included in that test program. The WOBE index range was from 45 to 56. Again, the focus was on carbon monoxide and NOx emissions, primarily from the point of view of safety, but also with regard to impact on the environment with regard to NOx, not only in the home for any in indoor air quality aspects, but also NOx being emitted into the local atmosphere. It was extended to actually include the impact of WOBE index changes on the performance of the safety control systems, particularly the flame supervision device or the oxygen depletion sensors that some appliances have. The efficiencies were calculated in the same way as before. But they added in an additional test here where the appliances were serviced, so that the tests were done and then repeated once they had been the appliance had been serviced, which could involve some maintenance work or some repair work, and the results were then the tests were then repeated with that serviced appliance. Next slide, please. So a quick example of the condensing boiler. Here it's got a premix burner, so it's the form of combustion that profile that I showed earlier, and you can see that from 45 WOBE index value of 45 up to 56 that the CO emissions increase. Again, the gas safety management regulation band is shown in the orange bars. And the trend is fairly clear from of increasing CO across that range. If you prefer the dry air free CO percentage to be at ppm, you're looking at a range there of from 0 to 400. So it's the values around the GSMR band at the moment range from around about 25 parts per million up to around about 75 parts per million. You may query why there are so many different points at around about 50.7. That's the G20 reference gas. It's pure methane, and repeat tests were done with those gases after every other Wobbe index gas was tested to ensure that there was no lingering change to performance or impact from running those tests. So it was a cross check that the appliance was still behaving and operating correctly. Next slide, please. The NOx profiles, as you can see, it's very similar to the ones that we've seen previously, increasing NOx as a function of Wobbe index. Next slide, please. For the open fluid boiler, the carbon monoxide, again, very low, within the range and at lower Wobbe index, and then starting to increase as you go to higher. But again, the fairly modest increases. Next slide, please. And again, with NOx increasing as a function of Wobbe index. Next slide, please. GasQual took the testing program to the next level, and it was evaluating the impact of gas quality on safe operation efficiency and emissions. 100 appliances were tested, a wide range of gas qualities. There were 16 companies involved in this from 9 countries around the EU, and 5 laboratories actually undertook a lot of the test work. Next slide, please. The project was split into several work packets, and they involved both a study of the appliances that were actually installed around Europe, and an understanding of the different gas quality regulations and gas specifications that were actually in force around the different member states. It also looked at certification and how the appliances were tested for use in those different countries, and also a look at how the appliances were installed, particularly with regard to were they adjusted and altered at the point of installation rather than use factory settings. Based on the range of appliances that were actually available, that sample of 100 were selected, tested, and then conclusions were drawn. And there's a bit of feedback to loop there to ensure that understanding of the results from the different tests that were undertaken were actually used to sort of fine-tune the testing program. Next slide, please. The appliances were categorized into 29 separate groups. These were based on the different certification standards that we use for different types of appliance. So you get a different EN standard that was used for certifying a condensing boiler compared to a cooker and an air heater, different types of boiler setups and the like. So a fairly wide range. And the number tested in each segment, in each of these clusters, was actually based in terms of the overall population distribution that was determined in that first work pack. So there's a lot more boilers, so they actually tested more boilers. There were far fewer tumble dryers, that sort of thing. Next slide, please. So you've got the test gases highlighted there with Wobbe index against relative density, the same sort of plot that Dave Landers presented, ranging from the one on the left-hand side being the G20, and then the test gases associated with a range of Wobbe index, and also exploring the impact of the different gases that might be available close to the 0.7 relative density value. Next slide, please. They produced a lot of results out of that project, but I think one of the highlights is the impact profile, the table on the left. Green essentially means that the appliances can cope with a wide range of Wobbe index. The Wobbe index is listed at the top from 46 to 54. or 55, and you can see that the bulk of the diagram, bulk of that table is actually green, which means there's no significant increase in the carbon monoxide emission as a function of Wobbe index for those particular appliances. There are a few that impact in terms of the amber that give warning that it's starting to increase, and then there are, as you go to the very high Wobbe index values, there are a few appliances that would actually give a red, which suggests that the CO level was slightly higher than was acceptable. For the eagle-eyed amongst you, you'll have already spotted that the top line says 1 adjusted, and followed by a second line being 1 non-adjusted. These were for premixed condensing boilers, and what these tests indicate was that for an appliance that was factory set, that's the line 2, the non-adjusted, and that's where it's set at 50.7 for the G20 test gas. That could accommodate the full range of gas qualities without significant impact in terms of operation. The adjusted ones were where the appliance was not adjusted to the 50.7, but one was adjusted to a very high value and then looked across the range, or one, and then readjusted to a low value and adjusted. And clearly, into those situations, the change in Wobbe index, rather than being 4 or 5 megajoules from top to bottom, as it were, was actually 8 or 9, and that's actually too great, as it were, a change for the appliances to actually accommodate. Hence, you would get those the red and the amber. Next slide, please. So you saw that the gas quality study ramped up from the DTI work up to 100 appliances. The opening up the gas market study actually went to over 2,000 in Auburn, and I think this constituted one of the most significant data sets, understanding what the impact is in terms of the appliances actually installed in people's homes. The testing covered both the high and low Wobbe index gases. Kiwa Gas Tech undertook a lot of the test work here. They did 18 appliances actually in their laboratory with some very detailed work, but they also undertook the tests in people's homes, as I say, by taking a bottle truck round to people's homes and testing with the 3 reference gases and limit. So with the reference gas and the 2 limit gases, the G20, G21 and G23. These are the test gases that are used to certify appliances. And they looked at what the impact was in terms of the performance of emissions of CO with the appliances actually in people's homes. And as I say, I think it's there to be applauded. It was an extremely good piece of work. There's also, in addition to that, ongoing spot checks to confirm performance for longer-term performance of these appliances as well. So not only have they got those one-off tests that they've done when they went to the people's homes, they've also got additional data to understand what the impact is in terms of the longer-term performance. And again, I think these data sets are some of the most significant ones that we've got open to us to understand what the implications are for gas quality. So very quickly, the next slide, please. The results show here that the variation in CO of those measurements that were made on the different appliances, the different appliance types are shown in the legend on the right. You've got over 400 boilers, over 200 boilers with a gas air ratio controller. There's a commercial fryer in there, flue space heater, and then the tumble dryer. And the tests were done using these 3 test gases. So you've got your 3 points, one at 45.7, one at 50.7, and then the G23 at 54.7. Sorry, G21, I do apologise, that's the richer gas. You've got the darker blue current GSMR values. You've got the lighter blue box that's actually the proposed easy gas European specification from 47 up to 54. And then you've got the exemption line that's highlighted at 53.25. The CO again is down the left-hand side axis on the y-axis, Wobbe index on the bottom, and you can see that the trends actually are for most appliances that the CO increases as a function of Wobbe index across that band, or is actually flat. And again, look at the CO values; they're actually quite low in terms of what's actually in the flue. So very good performance really across that whole range. Next slide, please. For the flueless appliances, the trends are very similar. There is one group that stands out as not being the same, and that's the commercial grill. So I'll put that one to one side and just highlight that the general trend is increasing CO as a function of Wobbe index, but the values are actually very low. I think from the test that's here, there's significant evidence to demonstrate that extending the range to what was proposed in Dave's presentation, down to 46.5 on the lower Wobbe index and up to 52.85 on the upper, is actually not going to constitute a significant increase in terms of the overall CO emission. Next slide, please. They also did some work when we were doing the open studies in terms of the impact of NOx. The blue line is with the appliance tuned to the G20 reference gas, and then the orange line was when it's tuned to 53.0 value gas. If you like, what happens there is that the excess air value is being adjusted, and what you can do is just slide the orange line and orange points to the left, and that 53 value overlays the 50.7 on the blue, and the trend then is the same for both lines. So I think the NOx emission is low again, from 20 parts per million at 45.7 up to around about 65 parts per million at the Wobbe index value. So these data sets are actually giving us confidence now in terms of what the performance is in modern appliances, with several hundred, if not several thousand type appliances actually being tested to actually understand what those impacts are. Next slide, please. So in summary, and just to wrap up, the practical tests have highlighted the general trends, and the general trends really are of increasing CO and NOx emissions with increasing Wobbe index, with one or two exceptions. However, the changes are actually quite modest. The tests on the installed and appliances in people's homes and the laboratory tests as well demonstrated that down to 45.7 megajoules per meter cubed, there's no significant changes in terms of overall performance. Again, there's one or two appliances that still buck that trend, but it's clear for a significant proportion that it holds. Increasing the Wobbe index limit to 52.85 will result in increased CO and NOx, but these changes are modest, I've already highlighted. And I think then we come to one of the key aspects. I think if appliances have been adjusted from factory settings, then this could give rise to more significant changes to emissions, and that's been highlighted in work that's been done. For the gas wall study, there's been also some demonstration of that in Denmark, where there's been some work where they found poor performance because they've reset appliances actually that are in the field. But within all of this, and I think it's highlighted with a lot of the test work that's been done, it's appliance servicing and maintenance of all those appliances is extremely important to ensure that performance is maintained across that Wobbe index range. Clearly, any misuse of those appliances or any damage could result in quite high levels of emission, and servicing and maintenance is then of key importance. That is all I'm going to present to you today with regard to the domestic data sets. I'm sure there will be lots of questions, so I'm happy to take questions now.
Thank you, Martin. What a good chat on the open study. chat on hydrogen blend as well. There's been questions which I think you could have answered as well, which has been around, you mentioned the plans have been correctly set up and maintained, and by who. You want to just add to that, Martin?
Sorry, sorry, I didn't catch that. Can you repeat?
So you mentioned about plans has been correctly set up.
Yes.
And maintained. The question was who by?
Well, that's a very good point, and that's something that I think should be considered in the future. We're not necessarily mandating that it's a legal requirement. We're recommending that appliances really are maintained, and gas safe engineers are more than capable to actually do those tests and ensure that that's the case. In terms of initial appliance setup, I think the manufacturers do an excellent job in terms of ensuring that the appliances are set for the appropriate gas quality, which essentially is a mid-range value. And if that's the case, then it does give you the ability, as it were, for that appliance to work right down at the low end, but also up to the high end in terms of the limits, in terms of what we index.
Okay, I just want to touch on some questions about NOx emissions.
Yeah. And
in particular, so looking at NOx emissions, if, for example, NOx emissions from typical appliances, if they reduce the lower lobby gases, does that mean that sort of hydrogen methane blends will reduce the NOx emissions from appliances as well?
That's a very, very interesting question. There's some contradictory evidence in the open literature about what the impact is of hydrogen. Hydrogen blends can actually give a decrease in NOx in some appliances, but an increase in others that have been published. And I know there's a lot of development going on with regard to NOx with hydrogen and hydrogen natural gas blends. Looking at the basic chemistry and looking at the basic flame phenomena, the flame temperatures are slightly higher for an adiabatic flame. That could potentially increase the emission of NOx with hydrogen. However, combustion is a highly dynamic and influenced by lots of different other factors other than the basic chemistry, how the heat transfer is done, where the combustion actually sits in relation to the burner and burner surface temperatures, what the flows are like within the appliance, what other heat transfer they've got. I believe there's potential for actually getting low NOx operation now with both hydrogen natural gas blends and also fully 100% hydrogen, although that's a bit out of scope for what we're discussing with regard to the overall natural gas quality here at the moment.
And just finally on NOx emissions, you mentioned about caused by higher lobby gases, there's likely to be a modest increase.
Yeah.
Is that likely to cause any compliance with eco-design issues?
I've got to hold my hand up there, Ian. I'm not sure. I don't think so. I think there's enough room between a lot of where the appliances currently operate to the proposed limit. Although I think with the eco-design and the future requirements for meeting limits, I think over a lot of our experience as combustion engineers, you find that limits get tighter and tighter and tighter. So I imagine that there's lots of opportunity for research to actually develop new systems for lower NOx operation. I think that's that's possibly the best approach to take. There's work to do, should we say? But I think there's a lot of very good work being done at the moment with regard to developing low NOx systems. I think the future is bright from a combustion engineering point of view.
Okay, thank you, Martin. I think that'll be it from your section. Now, in the interest of time, I think we'll move on to the next session. Please keep the chats coming in. We will respond to any questions that we don't get round to. We'll now move on to Sarah Kimpton. Sarah, over to you.
Thank you, Ian. Yeah, good morning. I'm going to talk about gas quality variations as they are in the gas networks now. and the work that we did on industrial and commercial customers and how they're affected by gas quality. So next slide, please. So the gas quality group established quite early on that all the previous evidence had been for domestic consumers, and that's quite correct for as far as the gas safety management regulations are concerned, because they are there to protect domestic consumers. But there's also a very important group of customers who also use gas, and these are the large industrial users and the power generation sector. Now, gas quality is very important for this group, so it was necessary to establish the current status of this sector. And many of these very large users are actually directly connected to the national transmission system and to the gas distribution network, so they have their own direct connection. And so we engaged with a number of trade associations, with users and manufacturers of combustion equipment on a one-to-one basis and in groups. And also we held a workshop at IGEM at which we explored the current and future requirements of this sector. We assessed all the responses. We also asked them about hydrogen while we were talking to them, although hydrogen is strictly out of scope for today's webinar. Next slide, please. So why does gas quality change? Many people think that the gas actually mixes when it's in the gas networks, and unfortunately this isn't the case. It travels in slugs with very, very little mixing except at the interface and then between different gas sources. So the gas sort of travels through the gas networks a bit like a train. It enters at a number of different points. So you've got St. Fergus, you've got LNG coming in at Grain and Southhook, you've got the gas coming in at Bacton in East Anglia. And it moves around in the NCS until it is taken out by a customer. So it's once the gas is inside the national transmission system or in the gas networks, it's very, very difficult to control who's getting what. The only thing is that at all the entry points, the gas is GSMR compliant. So any gas that you receive from the network will be GSMR compliant. So let's look at this example. Four little pictures you see in front of you. So on the top left-hand side, we have a low Wobbe index gas shown as blue and a high Wobbe index gas coming up the pipe just past that T. And you can see that the red gas or the high Wobbe gas starts to spill into the T, and there's a little bit of intermediate quality gas in there, which is a little bit of blending just at that interface. And then after 5 seconds, you can see that the high Wobbe gas has started to really spill into that T in a big way. And there's a little bit of mixed gas at the interface, and it's basically the high Wobbe gas is pushing the low Wobbe gas through the network as it's being taken out by a customer. After 10 seconds on the bottom left-hand side, you can really see that red gas. It's got quite well established flow profile. And after 25 seconds, I mean, that plot there is in a slightly different scale, but at 25 seconds, you can see there's a very well-established interface between the red and the blue gases with a sort of a plume intermediate to that. So if you were an offtake at the end of that pipe, for one moment in time, you could be taking a low Wobbe gas, and then over a period of, say, 10 seconds, you would then be receiving the high Wobbe gas. And there's very little that the gas networks can do about that, other than obviously assure you that both the low and the high Wobbe gas are GSMR compliant. So that is how it is now, and that's probably how it is going to continue. Next slide, please. So another thing to consider is that gas quality means different things to different groups. And here we've highlighted about 20 different properties of gas quality that various parties would be interested in. So if you're a producer upstream, then gas quality to you means making sure that the gas complies with the gas safety management regulations. So you'll be controlling sulfur, you'll be controlling hydrogen, oxygen, you'll be making sure that the hydrocarbon dew points and the water dew points and the Wobbe index are correct. And that will be your main concern if you were a producer putting gas into the national transmission system. If you are the national transmission system, then again, GSMR is your major concern. You want to make sure that all the gas within the network is compliant. However, if you're connected to the national transmission system, then it depends who you are, what you're interested in. So if you're a power generator, then the combustion properties are very, very important to you. So you'll be wanting to know about flame lift, auto ignition temperatures, flashback, and all those kind of things. And again, it'd be similar if you're running a gas engine. You'll be very, very interested in the methane number. If you were a storage operator, you'd be very concerned about hydrate formation and the energy content, because that's basically how you run your business. And if you are operating a gas distribution network, then CV is very important, because you need to control the CV within the network to ensure fair billing to customers. Domestic customers at the very end there are actually relatively tolerant to gas quality. And then also at GDN, at the gas distribution network level, you've got biomethane producers who are also putting gas into the networks, and their main concerns will be compliance with gas safety management regulations and CV. So it depends who you are, where you are, and what you're doing with the gas, and what gas quality might mean to you. Next slide, please. So although Great Britain is an island, we're actually very well interconnected with both Europe and Ireland and with the North Sea. So we've got connections with the North Sea. We've got the LNG terminals bringing gas in, which will be coming from the Middle East as well, and the interconnectors connecting us to Belgium and the Netherlands. We've also got Ireland connected to the NCS via Scotland, and indeed Ireland takes about 40 to 50% of its gas comes from the UK. So we have to be mindful of what we're doing in GB, because it impacts on other people and on our neighbours. Next slide, please. So what we did, we looked at the gas quality data in the national transmission system over the whole of 2019. We took the data from the Ofgem directed gas chromatographs that are at the NTS offtakes at intervals of about 4 minutes. Then we used a red, amber, green system to visualize the range of gas quality that was being received at an individual offtake, and also looking at the rate of change of that gas quality. So on the slide following, there's each part of the UK has got 2 circles on it. So a big circle indicates the range of the gas quality. So if you have a large red circle, it means that there's a range of more than 3 megajoules per cubic meters at that offtake in 2019. If there's a little circle, and then it means that indicates the rate of change. Now this was for 2019, and it will be different every year. There is no place on the network where the gas quality is always stable. Note that it also depends what you mean by stable. Are you talking about stable CV, or do you want stable WOBE index? They're very, very different. As an aside, the Federal Energy Regulatory Commission in the US recommends that the maximum rate of change for customers should be 2% per minute in WOBE index, and this equates to about 1 megajoule per cubic meter per minute. Right, I see we've already moved on to the next slide. So, for example, looking at this slide, if you look at Southwest England, there is a wide range of WOBE index on the image on the left. There's a wide range of WOBE index. We've got a large red circle, and we've got high rates of change. So we've got a little red circle within that big circle. But you can see, if you look to the picture on the right, that the CV range is not as bad as the WOBE index range, and the rates of change in CV are actually pretty low. So although the WOBE is changing rapidly and the range is quite big, the CV is actually slightly different. And again, if you look at Northern England, where you can see that the WOBE index is quite stable, you've got the 2 green circles in Northern, but the CV is much more varied. So you've got a wide range of CV and sort of medium variability. So this is a good example of what gas quality means to you. Depends upon what you're actually interested in. If you've got many different compositions, may give you the same WOBE index, but they won't necessarily give you the same calorific value. So you have to be very, very mindful about what it is you're interested in, why you're interested in it. And just reiterate that these images are for 2019. We've also done them for other years, and the pattern is very, very different. So there is no place in Great Britain where you can say the gas quality there is always going to be stable. This all depends upon the sources of gas, where they're coming from, how the gas is moving through the national transmission system. So it varies all the time. Next slide, please. This one's quite a complicated looking slide, but there's just a couple of things I'd like you to take away from it. The current limits on WOBE index are shown by the dotted black lines. So at the top you've got the higher WOBE index, and the bottom you've got the lower WOBE index. And what I've done here is I plotted the WOBE index against relative density, as Dave was explaining a little bit earlier. And if you look at all the gases in 2019, you can see that they all fit very nicely within that proposed diagram. Some of the gases, for example, in Wales, which tend to be the green ones, Wales and Southwest England, you can see have a very wide range of relative density, and there's other gases which have a wide range of WOBE index. But in 2019, gas was seen almost covering almost the entire WOBE index range that was allowable under GSMR. Next slide, please. So here's two power stations. We're just looking at one at the moment. So this is the one we're looking at, which is information that we received from National Grid. There are two plots of, at the top in orange is the WOBE index, and the lower one in blue is the CV. You can see that for power station A, the WOBE index and the CV range were about 2 megajoules per cubic meter over the whole year. And if you look at the two plots, although they're sort of similar in shape, they're not actually identical. So this is sort of illustrating again that when the WOBE index goes up, for example, the CV doesn't necessarily go up as well. It might go down. So there are a number of instances of that. If you just click again, please. We'll have a second power station coming on. Yes, the second one is another location on the national transmission system in 2019. And here you can see that the range of WOBE index received by that power station was about 4 megajoules per cubic meter. That's the orange plot at the top. And the range of CV was about 3 megajoules per cubic meter. You can also see some quite scary looking spikes in WOBE index and both CV as well. And so there was some very, very rapid changes in these properties. Just to emphasize, that is the gas quality and how it's varying now. So there is a little bit of a myth that the gas quality is relatively constant. It isn't. It's already varying quite widely, but it's all within the GSMR limits. Next slide, please. And this one's showing a little bit of detail about what was happening in Southwest England over a few hours in 2019. So this is results direct from one of the gas chromatographs there. So if you look along the bottom, we've got the time. It's about 11:16. We had gas A, and the WOBE index was about 48 megajoules per cubic meter, and the CV was about 40. At about 11:45, another gas came along in a slug, and the WOBE index increased suddenly and rapidly to about 50 megajoules per cubic meter, and the CV dropped. And then about 20 minutes later, we had another gas came along, and the CV dropped again, and the WOBE index increased almost up to the maximum limit. If you click again, please. Well, should show the gas composition. So I'm a little bit concerned here. My laptop is just installing some software. Don't know why. So you look at the gas compositions, you can see that gas A is a natural gas, but it's obviously quite a rich gas. It's got an awful lot of ethane in it, but in order to control the WOBE and the CV, there's quite a lot of CO2 and nitrogen's being allowed to be retained in it. Gas B is also a natural gas. You'll see that there's much less CO2 and nitrogen in that one, and the methane content's gone up. And gas, the last gas is a LNG, and you can tell that it's an LNG because there's no carbon dioxide in the gas. But you can see that there is about 0.8% of nitrogen in there. And if you click, yes, if you click again, you can see at the top that it's been ballasted with about 0.8% of nitrogen to bring it just under the upper Wobbe index limit. And if it weren't ballasted, it would have been outside of specification. It would have been a Wobbe index of 51.7. Next slide, please. So this is a summary of what the information we got back from our assessment and our discussions with the industrial and commercial consumers. So on the left-hand side, you can see how we group them. So we've got power generation, gas engines, industrial applications, boilers, storage, NTS compressors, because they're also gas turbines. There's some folk using natural gas as feedstock. And then there's also the industry, the supply industry, who are manufacturing control and measurement systems. If the other, you can see at the moment, the under current GSMR limits, there are fluctuations of up to about 3 megajoules per cubic meters and sometimes a little bit more. And you can see for the power generation and the gas engine sector, that would cause them problems if they didn't have control systems fitted. And once control systems are fitted, then they are able to manage this range of Wobbe and CV. For industrial consumers, like with very large burners, they're okay at the moment if their burners are set up in the mid-range of Wobbe that they're likely to see. So we'd probably recommend something like pure methane. If they happen to be setting up their burner in the field, as there's a gas passing at that point with at one of the either at the upper or the lower limit, they would have a problem. So this sector, it would be very, very important for them to actually understand what the gas quality is when they're setting the burners up. There's a couple of ways to do that. It will be really great if we could have a handheld CV or Wobbe index device, or some service maybe provided by the gas networks that someone could call and then find out what the gas quality is likely to be passing at that point at that time. The same is also true for large boilers. If they're not set up in the mid-range, then they could also be a little bit inefficient or producing more emissions than perhaps they should be. For the storage sector, chemical feedstock, at the moment they seem to be operating quite happily with the current GSMR limits. If we were to increase the upper limit to 52.85, you can see the power generation and the gas engine sector would have problems coping with that without control systems, but with control systems, then they are perfectly able to cope with that. Again, a similar problem with the large industrial burners. They need some way of understanding what the gas quality is when they're setting it up, to make sure that they're not setting it up when the gas passing that point is either at the upper or the lower limit. So, I mean, the main message to take away from this is that there is mitigation available, or could be available, for all these sectors, which would make it possible for this group of customers to use. However, we do acknowledge that for some sectors this could be expensive, especially for gas turbines, and there might also be limits on the allowable gas quality as far as their insurance cover from the original equipment manufacturers is concerned. So we do acknowledge that that is an issue. However, these are the factors that the HSE will be taking into account when they're looking at all the evidence before they're making their decision. So if you want to contribute to the consultation process, or you want to raise a particular subject, then please do respond to the consultation document that's currently out there and issued by IGEM. I think that's all I'm going to say now. Thank you very much.
Thank you, Sarah. Some chats have been around looking at some biomethane and potentially looking at fluid average CV and the effect of not ballasting LNGs with nitrogen. Would be useful to maybe look at that as a potential modelling exercise. What's your thoughts on that, Sarah?
As far as flow weighted average CV is concerned, there is currently a network innovation project being undertaken by Cadent, where we're looking at better ways of billing customers so that the bills that they receive is much more close to the gas that they're actually receiving. So we are addressing that, and if we can do that, then that would negate the need for biomethane to be propanated. It would also mean that if you had a very, very high CV gas or whatever, you would be able to get that in as long as it was within the GSMR limits. I'm not also suggesting that CV is one of the GSMR limits, but yeah.
Thank you, Sarah.
So yeah, we're looking at that.
Brilliant, thank you. Well, we'll move on to the final session now, and I'd like to invite Dave Lander back to talk about the network safety impacts, and we'll have a Q&A session at the end of that as well. Dave, over to you.
Okay, thank you, Ian. Could you have the next slide, please? Okay, just by way of an overview, I'm really just going to answer two questions which came up at an early stage during the activities of the working group. First question is really about flammability limits. So would the hazardous area limits and procedures for gas escapes, for instance, need to be revisited if the WOBE index limits were changed? Secondly, we had a query over pipeline fracture propagation. And essentially the really question is, would increase in the WOBE index limits result in an increased risk of fracture propagation increase? Okay, next slide, please. So as far as flammability limits are concerned, essentially flammability limits, would the hazardous areas limits and gas escape procedures need to be revisited? Well, essentially, these things are principally governed by the flammability and the explosion limits of natural gas that you convey. And for many IGEM standards, the lower and the upper bound flammability limits are just taken to be 5% and 15% gas in air. In practice, the flammability limits do vary considerably, and they've probably never been these values. Next slide, please. So here I'm just going to illustrate the variation that you see in UK gas quality. So taking the lower flammability limit, that varies typically from around 4.5 to 4.9%. So next slide, please. And you'll see that this traditional value that we take for LFL of 5% is actually quite way outside what we actually see. Next slide, please. And many of you will be familiar with the mean Bacton gas composition, which is a sort of taken to be a sort of representative of the early natural gases that came from the southern North Sea. And that mean Bacton gas composition has a lower flammability limit of 4.9%. Next slide, please. The current LNG that arrives at GB, that has a lower flammability limit that varies from around 4.64 to 4.9, but typically it's sort of quite a narrow band, and you can see that that's what causes the spike in overall gas quality in that area. Next slide, please. In fact, current worldwide LNG varies quite widely. You get some that centres around about 4.8%, and some of the richer LNGs tend to have a flammability limit that sits around 4.6%. And so when you look at the UK gas quality, what's happened is that it's been shifted slightly by the ballasting that we see in order to admit the gas with an appropriate WOBE index. So if you go to the next slide. What we've got here are typical sources of LNG, and what you find is that the ballasting does tend to affect the lower flammability limit, but it's not a great amount. So if you look at the grain and the grain ballasted composition, so typical compositions from grain, then you would see ballasting the gas so that its WOBE index goes from 52.19 to 51.25, gives a change of around 0.07% gas in air in the flammability limits. So it's not a great amount, but that causes the shift from the value for worldwide LNG to sort of a central value within the UK range. Next slide, please. So with the IGEM gas safety standards, then most often you consider the impacts at 20% of the lower flammability limit. As I say, based on traditionally, they would think of that as being 1% gas in air. And also, many of the IGEM standards use mean back-to gas as the basis for setting their standards, and the flammability limit of that is 4.9% gas in air. Next slide, please. So what that actually means then is, in practice, our safety margin isn't really 80%, which is 100 minus 20%. So if we have current UK gas quality, we're currently enjoying a safety margin of around 78 to 79%, 79.6 if we only considered mean back-to gas. But as we've seen, mean back-to gas is not really representative of UK gas nowadays. And for the LNGs, with quite a wider range of flammability limits, then the safety margin will decrease slightly from 77 to 78. So there's still quite a lot of overlap in what we currently enjoy in terms of safety margin, but in practice, the safety margin is not 80% and not that much different to what we are currently seeing. So we don't anticipate there being an immediate need to change criterion. Okay, next slide, please. The next question really then is pipeline fracture propagation. And the question really is, would the risk of fracture propagation increase if the Wobbe index limits are changed? Okay, so the key thing to understand here is that generally gas transmission pipelines tend to be constructed from high strength steel. They're generally preferred because the reduced construction costs and the higher capacity, because you can construct them at higher pressure and higher sizes, offsets the higher materials cost. However, you do have to consider the ability of such steels to arrest a propagating ductile fracture. They need to be tough enough in order to arrest a fracture that would be generally caused by outside forces. So if you had mechanical damage to a pipeline causing a fracture, then you don't want that fracture to sort of propagate indefinitely. And so your concern is to have steels that are tough enough in order to withstand that. Next slide, please. So essentially, pipeline operators tend to use a Patel 2 curve, what's called a Patel 2 curve approach, and they can use that to show that fractures will not propagate beyond a small number of pipe joints. And in order to do that, you compare the fluid decompression wave velocity, talk a little bit about that, and the crack propagation velocity. So essentially, when gas escapes from the pipeline, the fluid will drop in pressure as it escapes, and the pressure will fall within the pipeline itself. And the rate at which the decompression occurs is a property of the fluid. And the key thing is that if the fluid decompression velocity is larger than the crack velocity, then the crack tip stress, the stress at the tip, will decrease and the crack will arrest, and vice versa. So if the fluid decompression velocity is a lot lower than the crack velocity, then the pressure is maintained at the tip of the crack, and that will then make the crack propagate further. Okay, next slide, please. And so you can visualize that on a curve. And so first of all, there's the gas decompression curve. So we're plotting velocity. In this case, it's the velocity of the wavefront, the decompression wavefront, against pressure. And that's the grey curve, the grey solid curve. And then what I've got illustrated here is the fracture curve. So it's the fracture propagation rate and the pressure. And the red line is, the red and the green lines are for two different steels with differing toughness. Next slide, please. And in this slide, you can see for the red material, then the crack can propagate indefinitely because it sits below that gas decompression curve. So you have a situation in which crack can propagate. And next slide, please. And if you have a tougher steel, then you'll see that a tougher steel will prevent propagation. So you don't get into this situation where the stress at the tip of the crack is too high. Okay, next slide, please. So for this assessment, what we did was to compare the relative risk that would be posed by differing gases. So essentially what we did was to examine gas decompression curves for various gas compositions. So the gas decompression curve will be dependent on the thermodynamic properties of the fluid, as well as the starting pressure and the temperature in the pipeline at the time of fracture. Next slide, please. So the gases that we looked at are a set of pipeline gases from GB import terminals. So we had access to compositions that were characterized in quite fine detail by a consortium that was looking at hydrocarbon dew temperature measurements and calculations. And so that provided us with a set of gas compositions that were typical of that being imported into the UK in 2009. We also have compositions of LNGs, which are characterised by the NIC project opening up the gas market. We can use those when they're ballasted and unballasted. So those are all those compositions that are available in the report that forms part of the technical pack for the gas quality working group. Next slide, please. Okay, so so for the pipeline gases, this is the sort of behaviour that you get. And the first thing I need to sort of point out is that the fracture curve, the dotted line, is illustrative only, with an exclamation mark, because it's not intended to be a particular section of pipe in any particular gas transporters network, but it's just illustrative to show the principle that's involved in the Battelle method. So you can see here for these pipeline gases, the red line is the one that shows the greater risk of propensity, and the grey line is the lower risk of propensity to propagate cracks. And you see that the red line has a Wobbe index of 49.54, and the grey line has a Wobbe index of 49.45. And yet, beg your pardon, intermediate between that is the green gas, gas E, which has the highest Wobbe index of them all, which is 50.23. So there isn't really a clear pattern in terms of Wobbe index and propensity for pipeline fracture propagation. So next slide, please. And in this slide, these are for the LNGs that we looked at. And what I've got here are the purple line, the lower of the lines. You can see that's an LNG from grain, and it's also an LNG from grain that's ballasted. And if you look extremely closely, you'll see that there is a slight difference. There you can see a slight suggestion of a dotted line, but essentially the points are the same and the decompression curve is the same. And yet they've got differing Wobbe index. And if you look at another LNG, which is the Qatar LNG, that's shown by illustrated by the green arrow, and you'll see that that has a shift which swings to the left, shifts the velocities to lower velocities, and you can see that it comes much closer to the fracture line. And so what you can see from this, and you can see it with other compositions, is that ballasting doesn't actually change the risk of a particular gas. If a gas shows some propensity for increased risk, then ballasting doesn't in fact affect things at all. So it's not really a WOBE index issue. It's, as usual with a lot of gas quality parameters, they tend to be correlated with each other, and it's not necessarily a sign of causation. It's just the fact that they're associated with some of these gases are associated with high WOBE index. So if we leave the limit as it is and say admitted Qatar gas, adding nitrogen to it to ballast it to bring it down, its WOBE index down, would in fact not change the risk at all. Okay, next slide, please. So I'll just try and summarise these two questions then. The flammability limits, they vary widely for existing UK gas anyway. It was never as high, the lower flammability limit was never as high as 5%. And as a result, our safety factor was never really 80%. It was around 78% in the early days for mean Lacting gas. And for most unballasted LNGs, then it would change from around 78% to 77 to 78%. So there's not a significant change in our safety factor that we would enjoy with a different unballasted LNG. As far as pipeline fracture is concerned, then it's not really a WOBE index issue. It generally tends to be high density gases, which can be exacerbated by hydrocarbon liquid formation. So on those LNGs where you sort of shift in the curve, what's actually happening is the gas is entering a two-phase region, i.e. hydrocarbon liquids are dropping out a little bit, which increases the density, increases the decompression wave, or decreases the decompression wave velocity. And ballasting doesn't really alter that risk. And so it's not an obvious parameter to specify that would control that risk. So certainly WOBE index isn't an appropriate thing. It wouldn't prevent that risk from occurring. Existing compliant gases show varying risk, and the risk really is dependent on the pipeline properties and the operating conditions, as well as the gas fluid. And our recommendation from this is that gas transporters should continue to assess their assets for future supplies. They do that now, and so it's not a suggestion that the pipelines are currently at risk, and it's just something that they would continue to do. But what you can't do is rely on WOBE index limits as a control measure for that. And as I say, there's not really an obvious parameter that would control that. So you would have to just carry out that assessment when you foresee different gases entering. Okay, I think that's the end of that. So not sure whether any questions have emerged on the chat.
Thank you, Dave, on that one. I think you've got a very kind of comprehensive presentation there on the network safety implication. So admittedly, this may be the first time that people have seen the study that you've done here. We would welcome any comments you've got on that. Please fire them into us all. We'll get around to questions that we haven't answered at the end of the session, and we'll certainly feed them back out as well. If you'd like to go on to the next slide, we'll close out this particular session. The consultation is open now until the end of July, where we welcome any of your comments. Please go onto the website, please have a look at it. In terms of timescales, what will then happen is that we will then collate all the comments that we've got, we'll bring them back into the group where necessary to respond, to take into account anything that we maybe missed, and appreciate all your comments that you fed in today. Now that can take, depending on the number of comments we get, can take maybe a month, 2 months. And by the end of that period, we'll then have a body of evidence from the industry comment period, as well as all the studies that we've now collated, and we'll bring that to the Health and Safety Executive in the form of a bundle of safety advice and safety case information to support any of the changes that we've made. Now that can take us maybe up to something right around October, where potentially, depending on how things go with timescales, that could be a time when we could be looking at publishing the IGEM standard. At the same time, what's happening just now is the Health and Safety Executive will be consulting, and they're already beginning to do a round of interviews looking at the impacts of the changes that were being produced, and from that they will then carry out their impact assessment with a view to looking at then changing GSMR, which could take into anything to another sort of 12 months afterwards until that period is completed. But we will certainly look to complete this work as soon as we can, certainly after the consultation period has ended. So please go onto the website, please have a look at the comments, and please fire those comments into IGEM through the website, and we'll take them into account in our deliberations. And thank you to the presenters, to Martin, to Sarah, and to Dave in particular for the time today as well. I'll hand you back to Tom to close out.
Thanks, Ian. Just a few final remarks from me to again note that the recording and responses to the questions raised during the chat will be shared, and to reiterate Ian's request to respond and share your comments via the consultation process. To repeat the date, that's open till the end of July. And finally, from Energy Networks Association and the Gas Goes Green team, I'd also like to thank our speakers, Ian McCluskey, Dave Lander, Martin Brown and Sarah Kimpton. And finally, a big thank you to all of you for joining today and for your engagement. It's been a really interesting discussion and great to see all the engagement via the chat. And we look forward to seeing you at future Gas Goes Green and IGEM events coming up. So many thanks all, and have a good day.